Okay, folks, I guess we should uh, get going. I didn't know if anyone would show up tonight or remember Tuesday night, but I thought I should be here. Um, Obviously, we created some issues with the ANOVA example and the data set for that. And so, that's not going to be a part of that particular evaluation now. I don't know exactly what's going on there. I think the data file uh, I don't know. It may have gotten a little bit corrupted, or I may have pulled up the wrong version of one. Names are too close together or something. I don't know. But it worked fine until it got down, near the end. And I think the ANOVA was an issue. I'm not sure the regression was an issue. It could have been. But I think, I don't know, whatever.
Are
So,
there different versions of JASP?
yeah, there are. There are about, gosh, I know we're in 10th or 12th version I've worked with already. And
I didn't have, I mean, it worked for me.
yeah, okay. Well, sometimes it may be that, in sort of working with JASP, they may have, they're always recoding it as they add more elements to it. They're not supposed to make it so that it won't work with previous data or previous data file. But as many people are working on it around the world, and this is could be in any one of 300 or 400 different university settings around the world. It's hard to say what may have happened, and so we'll just not worry about that. I am working on in fact, I put up a data file that I'm going to use as an example tonight to talk through some of the ANOVA stuff just a little bit. And so I was going to record that, and then I thought, well, I'll just wait and do it tonight and record that. And, in no sense, kind of recording it twice. But if that was the only piece we had trouble with, then yeah, probably a miracle. But hopefully it was. I think you find the more that you work with this stuff, the easier it becomes, the more common sense it is. And, there are little nuances in terms of, what subroutines you turn on or what, things you do. But one thing about JASP is that it always defaults to what is the most common setting. And so if you accept all of its defaults, you probably will be okay. And there's just a couple of little things that you have to do. So I was going to work through an ANOVA analysis on this new data set, which is up on As You Learn, by the way. It's called the Adjunct Final. It's a data set from a piece of research that I did a bunch of years ago, probably 10, 12 years ago now. And well, actually it was 12 years ago because I was doing it when I left the community college. So, 12, 13 years ago. And we finally decided to make a presentation about it at AERA a few years back. And so I dusted it off, pulled it up, and did some analysis on it for AERA, and got, really nice reviews there and all that sort of stuff. And we had a journal that wanted to publish it. In fact, we had 3 that wanted to publish it. But my co-author, who was at the time a dean at the community college the data was from, was catching flack from her system office about, this piece of research that had been done at her campus that they didn't know about, which shouldn't have mattered because they didn't have to know about it. It was approved on that particular campus by their institutional review board. And so, she was afraid of how it might affect her career progress and that sort of stuff. So she asked me not to publish it in a journal, and I didn't. And So it's kind of laid there, that data set, but it's an interesting little data set. So I'm going to pull that one up. It's not health related. It's community college related. It's, you know, a lot of retention, GPAs, graduation, stuff like that, and different variables from the community college setting. But it does provide a nice example to look at ANOVA, and it also provides a nice example, you know, for a lot of these other routines too. So if we start working through that, let me see, yeah, there it is. Then we can kind of, you know, talk through some of the idiosyncrasies of ANOVA, and maybe some of the idiosyncrasies of any other routines you want to look at, if you want to look at regression or whatever. And we can, you know, kind of play with those things just a little bit. And at the same time, you know, I can develop this video that'll be a nice little learning process for that around this new data set. So you have any questions or comments or anguished screams or, you know, any of those things that you want to provide before I get into that? Okay. Well, then let me see, did I already load this thing? I thought I did, but I don't see it on my board down here. All right. I'm pulling the file up now that I just loaded up. It's at the end of section 6. It's the very last file in section 6. And okay, let me okay. This is, as I said, this is a file. Other glasses here I can't see with those. This is a file that was designed to look at the impact of the amount of adjunct instruction that new students had at the community college level, and its impact on you know, some retention factors like GPAs and retention for the first semester, second semester, all those sorts of things, cumulative GPAs, whether they actually graduated or not within a 3-year period with a certificate or a degree. And so it was a file that was built over 3 years worth of data, I guess starting back in about, well, I guess 2004, 5, and 6, maybe somewhere in that time frame. And the idea was that as we had, at that time, I was the institutional research director and VP for institutional effectiveness at that community college. So I had a dean that came to me and said, hey, I want to know if we can figure out whether using adjunct instructors with new students is disadvantageous to the students in terms of their long-term success in getting through the school, as opposed to using, you know, regular full-time faculty. And this had kind of boiled out of a debate that was going on about, you know, some personnel money and whether it should be used to hire adjuncts or whether it should be used to fill a couple of 3 new full-time faculty lines. And so there was a bit of a debate about it, and she was just trying, the dean was just trying to generate some data to see if there's anything that we could tell about that. And so it had, you know, all kinds of different data in it, and one that I want to use for an example, for an analysis of variance example, is their GPA in the first semester and the term that they started. In other words, there are 3 years worth of data here. Did the year that they started, 04, 05, 06, have an impact on their first semester GPA? Because we wanted to get a baseline as to what, you know, classes in college and classes in, well, in any school, high school, elementary school, wherever. There are variances between classes that go beyond just the demographics of it. You know, you get a class that seems to be pretty bright, and then you get a class that's very worksmanlike, but maybe not. You're not going to get the flashes of brilliance, and you know, you get kind of different classes in different years that they enter. And so the question was, okay, is there an impact on the first semester GPA that is the result of what term they started in, which year they actually started? And since there are 3 years here, we can't use t-tests, so we have to go to an analysis of variance. And on analysis of variance, there are 4 different routines. Most of the simple analysis of variance uses the regular ANOVA. And so, you know, that includes regular ANOVA and what's called factorial ANOVA. And so we're going to plug in the first semester GPA as a dependent variable. We're going to pull up the term as what's called the fixed factors. I mean, those are the things that they're not, you know, that's the givens. You know, what are the groupings? What are the givens? We're going to add descriptive statistics because we simply, you know, would like to be able to explain things a little bit better. Which one? I guess this one. And then we're going to add, make sure we're getting the right post hoc test on terms. Now, what is post hoc test? Since there are 3 groups here, the ANOVA will tell us if there are any significant differences between any of the groups. And it won't tell us between which groups. And so we have to do what's called post hoc testing. We have to go back in and kind of figure out, okay, you know, which one of these groups are different from each other. And so there's a routine called post hoc testing. Let me run this down a little bit. All right, this is the actual output here that we're looking at. And once again, it pulls out the most common setting. This happens to be a test, a post hoc test that assumes that the distribution of data is normal. In other words, that it meets the test of normality. And we have no reason to believe that it doesn't, so we'll just leave it at that. That's the model assumption. And then when we run the test, we get this output. The significance level is 0.019, which means that there is a significant difference within the groups somewhere, between groups somewhere. We can, you know, glance at the descriptives and see the 3 groups, 04, 05, 06. The mean values are relatively close. 06 is a little higher. The standard deviations are, you know, relatively close. The 06 is a little tighter and it has a smaller standard deviation than the other 2. And the ends are not exactly equal to each other, but they're all large, so we're not particularly worried about differences in n's. Yeah. So we know there's a significant difference. And the post hoc test looks at those differences between 0.4 and 0.5. What's the mean difference? There's a t-value, and the p, the significance level, is 0.84. So there's no difference there between 0.4 and 0.5. Between 0.4 and 0.6, there's a difference of about 0.2 in grade point average, a fairly big T, and it is significant. So we know there's a difference between 0.4 and 0.6. And that leaves only one difference to test, and that's between 0.5 and 0.6. And we get not quite significant. And so the only conclusion that we can come to out of this is that the grade point average in 0.6 is significantly larger than the grade point average in 0.4. So the 0.6 class had a little bit higher grade point average. And so when we do more analysis, there might be a slight bias that way, but it's probably not a big one because of the n's all being fairly large and those sorts of things. And so we would say, okay, well, this is a significant difference. It's between 0.4 and 0.6, those two groups, 2.044 and 2.064, and 2.064 is larger than 0.4, so therefore there is a significant difference. Now, okay. Now I'm going to show you something here that obviously won't be on test anywhere, but it is a useful sort of artifact here. If we wanted to know if we asked the question, was the grade point average in 2006, 2064, significantly larger than the grade point average in 2054? Now notice that is a directional one-tailed test. All we have to do to ask that question is to divide this p-value in half. So as a two-tailed question, is there a significant difference between the class 2054 and 2064 on grade point average? The answer is no. If we ask the more specific directional question, is 2064 significantly greater than 2054? Now we have a one-tailed test. We divide the p in half, and we get 0.048. And so it is a significant outcome for a one-tailed question, but not a significant outcome for a two-tailed question. And that's why I always tell students when you're doing research or when you're analyzing data, always ask one-tailed questions. Because one-tailed questions gives you a clearer view of what's in the data, but it also gives you a slightly more enhanced possibility that there's something significant there. Actually doubles the possibility that you'll find something significant if you do a one-tailed test instead of a two-tailed. Now, you might go back in here and run the same analysis, and I'm going to save this file out, and it'll be up on the JASP. In fact, this analysis is already in there. That's why you have two sets of tables here. I ran it before just to get it in there. And so you might run this same analysis again, except for the dependent variable. Choose one of these other GPAs. Choose GPA semester 2, choose cumulative GPA. There's a couple of those. There's a cumulative GPA semester 3. And so, you might run those again, this exact same analysis, except have a different dependent variable and see what turns up. Okay. Any questions? All right. Let's vary here a little bit. I said the ANOVA routine, the basic ANOVA routine, is good for two things. This is called a one-way ANOVA, where you have one independent variable and one dependent variable. And one independent variable has more than two levels. There's also what's known as a factorial ANOVA, in which you have two or more independent variables, and you have what are called interactions between them. And I just want to show you that. It's not going to show up. It's not going to be on evaluation, but I want to show you that and build that into this example so you'll have it when you might look at it. And let's say that we decided we also wanted to know whether gender had anything to do with this first semester GPA, along with which term it was in. And so all we do is we just add gender. In this case, it's called sex. Those are back in the old, politically correct ways of stating data. And so we'll add sex in as a variable. So now we have two independent variables. We don't really change much. The post hoc tests really are kind of not necessary unless we put them all over there. Okay. And the descriptives get a little bit more hairy. But now here's this new set of charts. When you have multiple independent variables, you can think of those as a matrix. And on the rows, in this case, would be sex. And on the, well, it could be the other way around. On the columns would be term. And since there are two genders and three terms, it would be a matrix that has 6 possible outcomes. Yeah. 2 of those outcomes, one of those outcomes you're already seeing, and that's term. And if you go back up and look at the p-value for term in the previous thing, it was 0.019. The p-value now in a factorial model is 0.013. So just as we figured, the term is still significant. That's called a main effect for term. The new variable sex is significant, less than 0.001. That's called the main effect for term for sex, and the interaction term is not significant. And so you have two significant main effects and a non-significant interaction effect. And it's called an interaction effect. Here's the 6 cells, female and male for 2044, female and male for 2054, female and male for 2064. And if you look at the differences, you don't see radical differences in almost all of them. You know, the male GPA is lower than the female. And so when we come down and look at the post hocs, we know this one didn't change. 2044, 2064, still significantly different. Now 2054 and 2064, divided in half, still significantly different if you ask the right question. And when we look at just gender, sex, we find that the difference between males and females, now notice this mean difference is a positive. So when we take the average female GPA minus the average male GPA, that's the difference, 0.243. It is a highly significant outcome. But the two things together are not significant. And so when you get to these post hoc comparisons down here, where you have two things together, you really don't show up anything that is much new here, except that in some of the cases, you get the female higher one reflected, like in 064. You know, the female is higher than the male in 44. And so these are a combination of gender and terms. And so this is kind of doesn't mean a whole lot, because we know this interaction effect up here, term versus sex, is not significant. So this table really doesn't mean much, doesn't tell us anything. But we do now know that there are two variables that are have significant differences on first semester GPA. And it tests three things, in this case, two main effects, main effect for term, main effect for gender, and then it tests the third thing is the interaction effect for the combination of term and gender. And that's called a factorial ANOVA, because you have two independent variables that you're looking at the same time. And the only difference in the setup is you just have to drop another term in over here in the fixed factors. And you have to go into the post hoc and make sure that all the other terms are in the post hoc. Any questions?
No, I don't think so.
Right. And when you look at it, you may find that, you know, you may have a question or whatever, and that's okay, pop it up. But just be aware the factorial thing is not going to show up in either any evaluation, final. This thing, the biggest thing, the only thing left really is the final evaluation after you get finished with a few small things. And it won't show up there. But I thought it was important that you need to know you know, that other methodology of using the straight up ANOVA. Now, we will come back with another video and we'll talk about the ANCOVA, which is the analysis of covariance, and what's called MANOVA, which is the multiple analysis of variance when you have more than one dependent variable. And so it's both of those are useful techniques to talk about, and I will put them in a video, but we will not necessarily spend a lot of time with those. And they certainly won't show up on any evaluation. All right, do we need to do a regression? Would that be useful? It's simple to do. We can do it quickly. All right, let me save this file out. And okay. I'm going to pull the same file up, but then I'm going to do a regression example on the back end of it, and I will save that out also and just call it adjunct final regression so that you can kind of see what's going on. All right, let me get over there, share over that thing. Okay. So what I did is I pulled down regression and linear regression. Correlations also in here, linear regression, which is what we're going to do, and then logistic regression, which is what we'll do in about a week or so. And I'll put up another video, another set of example stuff for that. But this is just straight up linear regression. Come on, guys, where'd I go? There we go. And one of the pieces of data that's in here is cumulative GPA semester 3. And so I'm going to make that the dependent variable. There's lots of different methodologies you can use. I like, you know, as to how you put variables in the equation. And so I'm going to put in credits completed during semester 1 and credits completed during semester 2 and see if they predict cumulative GPA in semester 3. Now notice I put in 2 independent variables. We could do just 1, we could do 2. I put in 2. Or we could do 3 or 6 or whatever. The same process works for one predictor, one predicted outcome. It's called linear regression, it's just called regression. For one outcome variable and more than one independent variable, it's called multiple regression. And it's exactly the same formulas and everything. In this case, I'm just adding a second one in there so we can kind of know what we're talking about. Now, the model summary, you are always looking at the alternative hypothesis instead of the null hypothesis. So if you're pulling numbers for anything, you're always looking at the alternative hypothesis. The null hypothesis just tells you, you know, if nothing's going on, this is what we think this might look like. If something's going on, that's what you're testing. And so we're always looking at kind of the alternative hypothesis to see what's going on. The ANOVA turns out to be significant. So we know this is a significant regression equation. The coefficients, unstandardized, for credits completed semester 1, credits completed semester 2, they are both significant. So both of those are significant predictors. And so we could say that the credits completed in semester 1 and the credits completed in semester 2 are both predictors of cumulative GPA in semester 3. So by knowing how many credits a person took in the first couple of semesters, we can predict what their cumulative GPA is going to look like. And I'm going to scribble some of this down on the notepad here because I'm going to go over the notepad in a second and kind of put all that together. Semester 1, 0.047. Semester 2. Uh, 0.019. Coefficients. Semester 1 is 0.15, 0.015, and semester 2 is 0.017, and the intercept is 2.79. Yeah, 2.79. Okay. So I'm going to leave this share and go over onto my little notepad thingy. And I have the p-values, so we'll know these are both significant. So we have 2 significant predictors, and we have an intercept value, and then we have what are called the coefficients that go in. And in this case, GPA, cumulative GPA, semester 3 is equal to, this is kind of like Y, is equal to 0.015 semester 1 credits plus 0.017 semester 2 credits. I'm just going to abbreviate, and plus the intercept, which is 2.79. So if we know the credits taken during semester 1 and the credits taken during semester 2, we can predict the cumulative GPA at the end of semester 3. And so let's say this is, I don't know, 6 and this is 10. Took an overload second semester. So do the math real quick here. Calculators still come in handy for something. This is 0.09. Seven times 10 is 0.17. Oh, shoot. 7 plus 0.09 plus 2.79 would give us an outcome of 3.05. So if somebody took 6 semester hours first semester and 10 semester hours second semester, we would predict that their cumulative GPA at the end of semester 3 is 3.05.
I've got a question.
Sure.
For the intercept number of 2.79, why did you use the H0 intercept instead of the H1?
Did I?
Yes, I think so.
Or did I? Oh, I did. I'm sorry. That's bad. Take, ooh, sorry. This should have been 2.51. I'm sorry. 2.52. So it's not 305. Now it's, how much is that off? That's 0.27 off. So, you know, it's 2.8, what? $2.78, something like that. Do the math. I don't do math anymore. But yeah, I used the wrong one, and that was my bad. I'm sorry. Yeah. Was that the only thing that threw you? That's the only thing threw you. I'm doing 100, okay? Because everybody's allowed, you know, my wife and I've been talking about there's always one thing. Nobody's ever perfect. There's always one thing. You know, it's you know, if you start looking at people, you say, I really like this person. I really like them a lot. But you know, there's one thing that bothers me. And I think everybody has one thing. Unfortunately, it's not the same thing all the time for that person. Yeah, but at any one point in time, it's only one thing. So yeah, let me make a couple of general comments about regression, because these are kind of important. Remember, this is an aggregate outcome. Does aggregate have 2 G's in it at the beginning? I don't know. It's an aggregate outcome. It's a group outcome. Among a group of students that had 6 semester credits in first semester and 10 in the second semester, we would expect an average outcome of whatever that is, 2.78 or whatever. That would be what we would predict to be their average income. Well, that 2.78, remember, is a part of a distribution, and it's in the middle, and then there's a confidence interval around it. So individual students could be anywhere in that confidence interval. So if we predict on average students that have 6 semester hours first semester, 10 the second, on average students like that are going to have a GPA, cumulative GPA of 2.78. That means that if a student's over here or a student's over here, they'll still would be within the confidence interval, but this one would be a lot lower and this one would be a lot higher. So the upshot is that you can never, ever, ever use aggregate data outcomes to predict individual performance. And we do it all the time. In the state of North Carolina, they use the EVOS system to, decide whether students got promoted or not, or passed a course or not, or whatever, or whether teachers got paid or not, got paid a bonus or not. And those were patently unfair because they were using a regression formula to predict what students would do this year based on what they did last year and the year before. And all that predicts is an aggregate outcome for a group of students that have the same characteristics. It doesn't predict individual students. And so you have to be very careful about, when you look at outcomes that you would predict, like if you look at babies, if you look at where they should be on whatever percentile chart you're looking at, whether it's weight or length or, whatever, those charts, where that line is on that chart, whatever you put that baby's point on that line, there's a confidence interval around it. And so you can't know individual outcomes. You can predict what they're most likely to be, but you can never predict individual outcomes based on aggregate data. Questions? I guess I should have finished this graphic up here by doing M1, X1, M2, X2, and B. So you get the Y is equal to MX plus B. You just have two X's, two pieces of data. But this is the most widely used stat in common everyday life. This is what we do to predict whether you're going to get a loan or not, predict whether you're going to get into grad school or not, predict whether whatever, or not. Predict whether your kid's going to get into the gifted and talented program or not. I mean, we use this regression model, for all kinds of things, and we violate that basic assumption that you can't use it to predict individual results. But we do use it on individuals all the time. And it's just it's such an easy model to access, but at the same time, it leads to a lot of inequities. Other questions about regression?
And you can do this, sir, with many different, you just don't have to use just two variables. You could do this with multiple variables. Yeah.
I used to do, when I was I haven't done any of this at App, but when I was at JMU, I was on a group that every 3 years, we would look at 3 years worth of admission data, the hard data points we could look at, like, class rank and SAT or ACT score, things like that, hard data points, average attendance over their senior year, things like that. And we could predict which students would do better their freshman year. And then that would go into the model for the admissions model for the next 3 years. And then at the end of that cycle, we'd pull 3 more years worth of data and kind of go back into it and tweak that model. Now, it wasn't designed to be the final determination. The final determination had to be based on recommendations and essays and things like that. But, you know, at that time, JMU, which had an enrollment of about, I don't know, 15, 18,000, was getting almost 50,000 applications a year for admissions. And, you know, unless you wanted to build a big edifice to put your admissions people in and hire another, you know, 100 people or so to do that, you had to make a cut somewhere. And so we built a formula that would, you know, cut people and kind of put them in a weighting category, and then, you know, give us a roster of, you know, 6,000 or 7,000 out of the 50,000 to look at the 3,500 we might admit eventually. And so, you know, we'd make a cut with it, and then they would decide who to admit. And there was all kinds of exceptions, you know, stuff like that. So it wasn't like if you were on one side of the line, you didn't get in. If you were on the other, you did. It was, you know, it was just used to help cut the workload down. But yeah, it's used quite often. You put as many factors as you want. Typically, you know, if you put more than 3 or 4 in, it gets a little messy trying to interpret it all. And so you know, you generally don't see regression models with more than 3 or 4 predictors in the model.
But you always use it to predict a final, like on this, we predicted the cumulative GPA. So you're always using it to predict a specific number of some sort.
Right. They're all continuous variables. There are no, when we look at logistic regression in a week or a couple of weeks or so, you will see that allows you to use categorical data to predict binary categorical outcomes. And that's a different way of looking at things. It's actually built on an entirely different model, but it looks very similar to regular regression. It's just using categorical data.
Okay. And ANOVA is just used to determine relationship between, not to predict a specific number or anything like that. Or ANOVA?
Yeah, just to look at a relationship.
Relationships.
We do consider ANOVA to infer causality.
Oh, okay.
We don't we don't construe correlation or regression to talk about causality. They talk about prediction, which is a different animal.
And is there a certain, like with the ANOVA, you have a certain percentage that you can be sure of your relationship, you know, 95% sure of it. Is that true for this too, that you can be 95% sure that that GPA is probably what you're going to get based on the other factors you put into the formula?
It's the average for a group of students having those characteristics.
Okay.
Yeah, and you can be, you know, 95% sure that that's the right average for a group of students having those conditions. You just can't predict individual students. So how are we going, folks? You okay?
I think so.
We got a couple more weeks before actually the final stuff will go up end of next week. I'm retooling that a little bit and you know, making sure the data sets are what they need to be given the experience of the ANOVA thing here. I actually do think the version of JASP created some issue there, probably looking at something that it hadn't looked at in the past or whatever. But, you know, I'm still trying to figure that out, but I'm just going to use a new data set and new analysis from here on out. And then that way we won't have to worry about that.
So, Dr. Bolt, the current evaluation, you want that submitted as 6 separate documents, right?
Right, each one's a separate one.
Okay. If we've already done it using that data set and didn't have a difficulty with the regression or the
Put it in there, yeah.
Okay, that's fine.
Yeah, I'd like to know, I want to look at it just to see, also just to see if there is, you know, a difference that is noticeable. And I think your question was about the hypothesis, wasn't it?
Yes.
Yeah, it really was. It ended up being about the hypothesis, and I told you the wrong thing, or I didn't know. Actually, the example I gave you didn't have the two hypotheses on there, did it?
Right. And so I just got a different looking
Yeah.
data set, and I just want to make sure that it was still, but now after we did this example tonight, it makes a little more sense because your example didn't have the two different hypotheses.
Yeah, and that was an earlier version of JAS,
Right.
which didn't present those. Yeah.
I realized that as you did tonight's example.
Yeah, I should have caught that, but it just, I would just glance through those tables and I thought, well, okay, that looks right. But I didn't. So, yeah.
Dr. Bolt, when I submitted mine, I did all of them on just one big Word document. You want me to go back and break it all up for you?
That'll work. That'll work.
You sure?
Yeah.
So I can go back and break it up. Okay.
Yeah, I'm not that picky.
Okay.
Yeah, I just thought people might want to do them along and not do them all at once and things like that. And so that's the reason I said you could submit them as 6 different things. When you finish one of them, you just pop it in there and, but one big one works too. I mean,
I have a question about the ANOVA. If we had trouble getting it to work in JASP, are you going to upload another, data set and another assignment for the ANOVA portion, or is that part just not happening anymore?
we're going to slide on by that one. Yeah.
Okay.
Yeah, hopefully this example we did tonight and this new data set, if you want to go back in and run it, with different outcomes and things like that, you may get, you may find that that helps a little bit. But yeah, it's pretty straightforward. And I'll put that data set up. In fact, I've already put the one with the ANOVA up. I just haven't put the one with this regression up. So I'll put a separate one up that says adjunct final / regression or whatever, which would actually have all the ANOVAs on it too, I guess, because I didn't cancel any of those. So we're okay? Any other questions? Now I'll be gone the next couple of days. I'm it's the last memorial service attending, and it's kind of a big one. So I'll be kind of incommunicado for a couple of days, trying to go to a place where there's going to be a lot of people around and socially distanced. And I have my heavy duty mask for this one with the N95 filters on it and the whole bit. I look like the space guy or something like that. But it is family, but I'll be damned if I'm going to catch some illness just because it's family. I made it to 70 in pretty good shape. I don't want to have anything happen at this point. So, other thoughts, other questions? All right, I'll put this data set up. Don't worry about the ANOVA. And then when I get back over the weekend, I'll probably put up a couple of other things that we'll start to get into next week, a little bit more with dealing with categorical data. And so we'll play with chi-square and we'll play with logistic regression, and because that's a different logic set, but it ends up looking a lot like what we've just dealt with, but it's an entirely different logic set. So I need to do a little bit to lay the ground on that. So I'll put up a couple of videos on that, and then next week we'll talk about using categorical data.
Very good.
Okay. Anything else?
No, I think that's it.
All right.
Thank
Have a
you.
good one. Stay cool, stay safe, and have a good weekend. And
Thank you very much.
I'll be back in the regular time slot next week on Wednesday, and we'll have a couple of videos up before then, so we should be able to move right along.
Very good.
Thank you.
Thank you very much.
Night, guys. Have a good one.
Take care.
Bye.
Thank you. Bye-bye.
Bye.